get started. I think now we have seen the basics for the parallel plate and the rectangular waveguide. Right. Now we are going to just plug a few holes that we have overlooked, all right, and that we are going to do by a combination of two things. We are going to use Octave to visualize a few things, right, and we are also going to make some arguments based on analytical formulation, right. And the two things that we are going to be talking about, right, one is with regards to the phase and the group velocities, right. The second thing is related to dispersion. Right. So, I am going back to the derivation that we had for the parallel plate waveguide in order to pick up one formula that we had, all right, and I have here the expression for the phase constant within the waveguide beta w, right, and it is beta 1 square root 1 minus m lambda 1 by 2d square. Right. So, I will go ahead and begin the lecture with that. Right. So, I have beta w. So, beta w is the phase constant of the waveguide is equal to beta 1. Beta 1 corresponds to the phase constant that is filling the parallel plate. Okay. So, it is the homogeneous medium that is filling the parallel plate. If it is vacuum, you will have the phase constant of vacuum square root 1 minus m lambda 1 by 2d square, where lambda 1 is the medium, all right, in the homogeneous medium that is filling up the waveguide. Okay. That is lambda 1. And then you are having d, which is the separation between the two plates, and m corresponds to an integer that will tell you about the number of half cycles of the electric field you will have in the transversal directions, right. So, we start with this, all right, and then we will slowly build up to some holes that we need to plug in, right. The first thing that we want to talk about is the velocity. All right. Now, I am going to make a clear distinction, okay, and I am going to make a distinction between two quantities, phase velocity and group velocity, and I will also show you how they differ, right, visually, right. So, the term that we have been seeing as velocity in the case of transmission lines was omega by beta, and then we went to plane waves, which was again omega by beta, and now also we are dealing with omega by beta. All right. This omega by beta is known as phase velocity. It tells you how fast the phase travels. It means that you will pick up a point in your sinusoid, right, corresponding to a particular angle. Say you pick up a peak, and you say that if your wave is a cosine, and you say that that angle could correspond to a 0 degrees, and you track that particular peak, how fast it is traveling, then that would be your phase velocity. All right. So, you are saying that the phase angle is traveling through space under your consideration with a certain velocity. Okay. So, the phase velocity is just telling you how fast the phase is traveling within your space a given amount of time. Right. So, here we are just talking about omega divided by beta, okay. And in this case I want to talk about the phase velocity in the waveguide, all right. So, I am just going to make this beta w, okay, and I have omega divided by beta w is gen beta 1 square root 1 minus m lambda 1 by 2d square. Okay. Now, omega divided by beta 1, omega is the angular frequency of the wave that you are passing through this waveguide, beta 1 is the phase constant of the homogeneous medium, omega divided by beta 1 is going to be the velocity in that free space medium, all right. If you are considering that you are having two parallel plates and you have free space or vacuum in between, omega divided by beta 1 will correspond to the velocity c. Okay. So, again you can say that this can be written as v 1 divided by square root m lambda 1 by 2d square, where v 1 is the velocity in the medium that is filling up the region between the two plates in the parallel plate configuration. Okay. Now, there are also a few other things that we have to look at, all right, before we get to the visualization part. Okay. Now, from the previous lectures, right, okay, I have also written down an expression for cutoff wavelength, and then I also wrote down an expression for cutoff frequency. Said that in order for your wave to have a propagation constant that is real, right, through your waveguide, you need it to be at a frequency higher than the cutoff frequency or a wavelength that is lower than the cutoff wavelength. And we had written the expressions in the prior classes. Instead of copying, I have to scroll a lot of pages, so I'll just write down the expressions that we had, right. So I had lambda cutoff is 2D divided by m, and the expression that I had for the frequency is mv1 divided by 2D. So, for your wave to travel, right, you needed to have lambda less than lambda cutoff or frequency higher than frequency cutoff, right. So, cutoff frequency. This is what we have seen. So, hence now I can go back to my expression for the phase velocity, okay, and rewrite the phase velocity, right, in terms of lambda cutoff and frequency cutoff. So, if I have a look at the expression has 2D divided by m, all right. So, it has m divided by 2D coming into the picture. So, I can just say it is lambda 1 divided by lambda cutoff the whole square. So, I can make a simple substitution and write this phase velocity in terms of the cutoff wavelength. So, I can say that the phase velocity is going to be equal to V1 divided by square root of 1 minus lambda 1 okay. I have a ratio of wavelengths. So, I have lambda divided by lambda cutoff. I could also write this ratio in terms of frequencies assuming a velocity. Okay. So, I can just write this in terms of cutoff frequency and frequency divided by f, all right. F is the operating frequency, right, frequency of your signal that you are using. F cutoff is determined by the dimensions of the waveguide, right, and the mode that you are choosing. So, F cutoff is m V1 divided by 2D, depends upon the medium that fills the parallel plate, depends upon the mode they are choosing m, and depends upon the construction of the parallel plate, that is the how far away the two plates are going to be, all right. And F is the frequency that you have chosen to operate it with. As long as it is higher than F cutoff, you will be having waveguiding action, right. Now, we have to see a few things after we have written down the phase velocity in this format, all right. The first thing that we see is the phase velocity okay, is a function of frequency. Phase velocity is a function of frequency because I have left hand side Vp, on the right hand side I have in the denominator f, all right, which is the frequency that I am going to operate. That means the phase velocity is a function of frequency, yeah, all right. So, if you have different values of frequency coming into the right hand side, you will end up with different phase velocities consequently on the left hand side, all right. Now, this means that the phase velocity is dependent upon the operating frequency, and such a condition, all right, where your velocity, the phase velocity is dependent upon the operating frequency, we call it as a dispersive medium or a wave dispersion. Okay. So, okay. So, you could actually have a parallel plate configuration with vacuum present between. We know that vacuum is a medium where we consider the speed of electromagnetic wave for all frequencies to be constant at 3 times 10 to the power 8 meters per second, all right. Even if you did do that, what will end up happening is, if you are going to choose a frequency where your construction of the parallel plate acts as a waveguide, that is, you are choosing a frequency above the cutoff, right. Even though you have used a non-dispersive medium, you will end up having dispersion simply because of the waveguide construction itself, right. So, a homogeneous medium that is otherwise non-dispersive, okay. In the case of vacuum, the phase velocity is just omega divided by beta, it is a homogeneous medium, all right. It does not have any frequency dependence, all right. So, it is going to be a fixed number, okay. So, what happens here is, in the case of the waveguide, you will end up getting dispersion for medium that is otherwise non-dispersive. This is the first thing that we have to look at. The second thing, and the more interesting thing, is that as the operating frequency increases, let us say it goes all the way to very high numbers, and I call this as infinity, as the frequency is very high, okay, Vp becomes equal to the V1, right. Vp is equal to V1. So, f is very high, infinity. So, that term becomes divided by infinity, so that is 0. So, V1 divided by square root 1. So, Vp is equal to V1, right. But at all lower frequencies, I notice that Vp is actually greater than V1, okay. It is V1 divided by square root 1 minus some quantity, okay, which means that your denominator is going to be less than 1 and your Vp is going to be greater than V1, all right. That is the reason I want to make a clear distinction with the phase velocity in the case of the waveguide. The phase velocity looks like it is going to be greater than or equal to V1, okay. But many times understanding this and making some logical interpretations of this will become very difficult, okay. That is why we need to now figure out what this phase velocity actually means in the engineering realm and how we can put a correct visualization to understand this, right. So, first of all, we can write down a few things and then fire Octave and see what happens, right. So, the general notion here is that the phase velocity does not convey this is what normally we say, phase velocity does not convey information, but what does that mean, right? We have to understand. So, in electrical engineering, especially in the undergrad, you would have had some courses which deal with the fundamentals of communication, where you would have talked about, say, amplitude modulation, frequency modulation, etc. And there could have been advanced courses which teach you about different digital modulation formats, etc. Right? But we are going to take the simplest case. In order to communicate information, all right, the electrical engineers would use what is known as a carrier signal and then a modulating signal, all right. You will have a carrier signal and then you will have a modulating signal. And in the case of the simplest scenario, so we will take a simple scenario, right. Okay. Let us say that I want to convey an information which is of a single tone or a single frequency, all right, and I want to use amplitude modulation because that is the first modulation format that you actually learn in your undergraduate, right. So, I want to be able to use amplitude modulation. So, I will be having a wave, all right. I am going to superimpose another wave because I want to do single tone modulation. I just want to convey another sinusoid using this carrier. Okay. This is the case that we are considering. So, I want to do single tone amplitude modulation. Okay. And so, you need at least two waves to achieve this. You need something which is known as a carrier and the other one which is going to modulate this carrier with the information that you want to transmit, and the information that we want is a single tone. So, it is going to be a sinusoid of some frequency, that is what we want to communicate, alright. So, you can achieve it using two sinusoids. One is a carrier and the other one is a modulating signal, that is all, right. So, what would the mathematical formulation be? Now, let us try to see what we have already learnt and try to put it in a perspective over here, right. We have seen that a forward travelling wave would be represented by, say, e to the minus j beta z, alright, and then you will be having a e to the j omega t coming into the picture with respect to time for a sinusoid. So, you can say e to the j omega t minus beta z, alright, and the real part of that would be a cos omega t minus beta z, and the imaginary part would be a sin omega t minus beta z. Okay. This is what we have already learnt in transmission line, plane waves, etc. Right. So, let us say that I want to transfer information from a source to a receiver, and I am going to use a forward wave from the source going to the receiver, and I just want to track the real part of it. Okay. So, what I am going to do is I am going to write down some expression. So, it is going to be a cosine. Okay. Okay. Now, I am saying that as in the simplest case, a single tone amplitude modulation can be achieved by two sinusoids. Okay. Now, instead of looking at it as omega t minus beta z, okay, let us say that I am going to pick up two sinusoids of two different frequencies and two different wavelengths, alright. So, I am going to make this a little bit clearer. You cannot say just two sinusoids, they could be just differing by phase, alright. So, I want to be clear, two different frequencies and of different wavelengths, that means different beta. So, I am choosing two waves of different omega and different beta. Okay. Now, I am going to say that in order to highlight this difference, I am just going to use some delta omega and delta beta difference between the two waves. So, what I am going to do is I am going to take two waves, alright, and I am going to write down the expression, right, omega plus delta omega times t minus beta plus delta beta z. So, I have omega t minus beta z form. One of the waves or the sinusoids that I am using can be written as omega plus delta omega t minus beta plus delta beta z. Okay. And I am going to use another sinusoid, and I am just representing it as omega oops. Okay. I am having two sinusoids of slightly different frequencies and slightly different wavelengths, and I have just added them up together. Okay. So, one of them should give me information about the the resulting expression should give me an information about the carrier and the modulating signal. So, all I am doing is I am taking two signals, I am just adding them up together. Okay. The two signals are slightly of different frequencies and slightly of different wavelengths, right. Now, I can use some trigonometric identity. So, this is of the form cos A plus cos B. So, I could simply use 2 cos A plus B by 2 cos A minus B divided by 2. Okay. So, I could use this formula to expand what is happening over here. So, I end up getting 2 cos A plus B by 2 here would be omega t minus beta z, right. Cos A minus B divided by 2 will just become cos delta omega t minus delta beta z. Okay. Now, I can see that I started with two waves of slightly different frequencies and wavelengths, added them up together, and I could also rewrite alright, the same expression to be a product of two sinusoids, alright. The first term is a cosine which is having omega t minus beta z. We are very familiar with this. This is representing a wave that is traveling in the positive z direction with respect to time. It is a forward wave, alright, cos omega t minus beta z multiplied with cos delta omega t minus delta beta z. Okay. Now, if I were to take these components individually, I could say that the first sinusoid is having a phase velocity of omega divided by beta. The second sinusoid or the cosine here, right, is having a phase velocity of delta omega divided by delta beta. Okay. Now, the real question is omega divided by beta and delta omega divided by delta beta, are they very different? Are they same? Do they convey the same information? If they do not convey the same information, which one conveys the information, etc., all these things start to come into the picture, alright. So, what we are going to do is, we are going to take this expression and we are going to try to plug it into Octave and see what the visualization looks like and what conclusions we can draw from there, right. So, I am going to fire Octave. Okay. And I am going to start with definitions of the terms that I want in that expression, alright. First of all, I am not going to use 3 times 10 to the power 8 meters per second to be the velocity. I like to use the velocity to be equal to 1 in air, and then everything is relative to that. But currently I am worried about vacuum, because anyway it is a non-dispersive medium and it could fill a parallel plate, it is a perfectly valid medium. So, in some normalized units, I am just taking c equal to 1. This means that I am considering only epsilon r and mu r. Okay. So, 1 by square root epsilon r mu r, where epsilon r is equal to 1, mu r is equal to 1, right, is just giving me a relative velocity of c equal to 1, right. And I would need lambda, considering it as 1. Okay. I want to calculate the frequency of this wave. I can just do c by lambda. The frequency of operation is, say, c divided by lambda. Okay. And in order to use the formula, I need also to find out beta and omega, alright. So, beta is equal to 2 pi divided by lambda. So, given a lambda of 1, I can say that my beta is going to be equal to 2 pi, right. Omega is going to be 2 times pi times f. Okay. One more thing that I will need in the way I have written the modulation problem is delta omega and delta beta, alright. So, since it is delta omega delta beta, I am going to consider some small values of delta omega and delta beta, right. So, I am just going to say I will consider delta beta is equal to, say, 0.2, right, and then I will say delta omega, let us make it 0.2 also. Okay, you can play with these values and we can see what happens. And I also have cos omega t minus beta z. So, I need to construct a space in z direction, alright. So, I am going to assume some 20 points or 200 points in z direction and see what happens. So, I will just go with z is going from z is an array, just going from some 0 to 20 units. Okay. And I want to see the evolution with respect to time. So, I am going to take some time is equal to 0, also 20 units of time. Right. Okay. So, I am going to write down the expression for the first wave that I am using. I am going to call that wave as A, and I have cos omega it was minus delta omega multiplied by t minus okay. So, I have cos omega minus delta omega into t minus beta minus delta beta into z. This is one wave, and the other one was having omega plus delta omega and beta plus delta beta. That is what we had chosen. So, I will just copy paste this line and I will make some changes. So, I will just call this wave as B, let's make it plus. Okay. So, we had two waves and we were just adding them up. So, I am just going to do C is equal to A plus B. So, I am going to create two plots to highlight the differences between A and A plus B. Okay. So, I am going to have two plots, one on the top and one on the bottom. So, first I will just plot the wave A, that is equal to some cosine of omega minus delta omega to t minus beta minus delta beta into z. It is just a wave. Okay. And I will have another plot at the bottom and I will plot the sum of these two for all instants of time, right. Since I want to see the evolution with respect to time, I want to give a small pause command, right. Okay. And I am going to run this program, right. There are two things that I noticed. The top one is a simple sinusoid. We know that it is moving forward in the positive z direction with respect to time, all right. So, the top one is just some omega t minus beta z form. The bottom one is a combination of the two waves that you have considered of slightly different frequencies and slightly different wavelengths. You have added them up together and I noticed that there is a difference and a commonality between the two. The commonality that I see is phase velocity, all right. If I take a point on the sinusoid on the top and see how it is moving, if I see a point over here and see how it is moving, they are going to move in identical ways, okay. But because I have added another wave, there is also some information that is coming in as the envelope of this signal, all right. And we usually say that the envelope is the one that carries the information, all right. You could say that perhaps this entire region could correspond to some information corresponding to bit 1, something like that, all right. So, you can say that that information has got so many waves, all right, but the envelope is the one that is actually conveying the information in the most elementary case of amplitude modulation, okay. So, once again I will run this, all right. So, I think in the bottom figure one should understand that the phase velocity is the velocity with which you are tracking a particular angle and it is how fast it is going in space with respect to time. The group velocity is actually going to tell you something about how fast this envelope is going to be traveling, okay. So, this is the distinction that people can make between phase velocity and group velocity, okay. Group velocity tells you something about the envelope that actually carries the information, right, and phase velocity is simply the oscillations and you are just tracking a point of constant phase, right. So, it is a very simple example. And you can also play around with these numbers. For example, you can make this 0.3, 0.3, etc. Right. Right. Then you will notice, if the beta became higher, so you will notice more modulation with respect to space, right. I can also make them, you need not make them equal, you could also make it like for example 0.2, 0.3 etc. You could also make them, you will notice some drifting patterns etc. But right. So, you can go back, play with it, but this is the most elementary form of modulation that we start learning in the communication when we want to transmit some information. That is, there is a carrier and there is an envelope to the carrier, and that envelope is the one that is carrying the information, right. So, now we go back and we have a look at our waveguide scenario in a similar manner, right. Right. So, I can now write down the phase velocity of this entire combination. Right. Right. Phase velocity is omega by beta, that is how fast your point of single phase is travelling through the space with respect to time, and then there is another term which is actually telling you how fast the envelope is moving, all right. So, I can just write down that is coming from the second sinusoid. You can also call that as the phase velocity of that particular term, all right. But in this case we are calling it group velocity because it is telling you how fast the velocity of the modulated signal is going from one side to the other side. So, it is delta omega by delta beta, and you could also choose very small difference in frequencies and wavelengths. For example, your delta omega could be very small, delta beta could be very small. You could mix those two signals and you will end up sending information. Okay. So, we can say that you could just write this as d omega by d beta. Okay. So, there is a difference in the way we have written. So, phase velocity is omega by beta and Vg is equal to d omega by d beta. You could always take the expression that we have written for beta for the waveguide and do a d omega by d beta, all right, or you could do 1 by d beta by d omega, it is up to you, all right. So, we have the expression for beta in terms of omega, you can differentiate the two sides and you will notice that Vg for the waveguide will look like V1 square root 1 minus okay. Let me just show what we had for the phase velocity. For the phase velocity we had Vp is equal to V1 divided by square root 1 minus f cut off by f square, all right. But if you did use d omega by d beta, you will end up getting Vg, and that is V1 multiplied by the same term. So, there is a difference between phase velocity and group velocity, and let us look at the obvious differences. The obvious differences that we can look at is what we did for phase velocity as f increases. Let us say it goes all the way to infinity, very high values, right. As f goes to very high values, values much higher than the cutoff frequency. Okay. So, you will have this term becoming 0, your Vg is equal to V1, all right. So, at infinite frequency you cannot distinguish between phase velocity and group velocity. Okay. The second thing that we notice is for all other f's lower than infinity, all right, all other finite values of f, right. We notice that Vg is less than V1, okay. So, square root 1 minus something, all right. If your f is finite, you will end up getting V1 square root of something which is less than 1, right. So, you will end up getting Vg less than V1. This is in stark contrast with the phase velocity. So, here we are saying that the group velocity in general is going to be less than equal to the velocity in the homogeneous medium. Suppose you constructed with vacuum, group velocity will be less than the velocity in vacuum for the same signal. Okay. So, it is not uncommon to have phase velocity higher than velocity in the bulk medium, all right. That does not signify that you are transmitting information faster or anything, it just means that phase is changing fast, but the information is always traveling at speeds lesser than equal to the speed of light in that medium, right. And if you consider that medium to be vacuum, information cannot be transmitted in vacuum at velocities higher than the velocity of the electromagnetic wave itself. Okay. So, it is perfectly fine to have phase velocities higher than the velocity in the bulk medium. That does not mean you have overcome speed barriers, all right. That does not mean you are entering into some domain where you are traveling faster than the speed of light and all that, no. Group velocity is the term that actually dictates the information content that you are trying to send, and the information content has an upper bound for the velocity. Okay. So, we are having Vg less than or equal to V1. Now, with this idea, let us expand or write another simple program to just see what is happening with Vg and Vp. One of the things that I notice common between Vg and Vp is that at frequencies which is infinite, both of them asymptotically come to the velocity in the bulk medium, in this case V1, all right. The second thing that I notice is Vp is operating frequency dependent for a waveguide. Vg is also operating frequency dependent for a waveguide, all right, just that the way they are dependent seems to be slightly different, but let us make a plot, okay, and see what happens with the modes of these, what happens to the phase and the group velocity, right. So, I am going to open Octave again, maybe I will just write a new program. Okay. Once again, I am going to take some variables that I will need to draw this, all right. I have the formula which says that I need to be able to define V1 for both phase velocity and group velocity. I also need the values of f cutoff f, that is all. Okay. So, I will go ahead and say that I am going to assume V1 to be equal to 1 vacuum, all right. So, in some relative terms I am using some medium, so speed is 1 over there, right. I also would like to give more information, right. Lambda 1 equal to 1, can also calculate beta 1 in that medium to be 2 pi divided by lambda 1, right. Okay. And I think the formula needs, okay, for finding out the f cutoff, I could use m V1 divided by 2d. So, V1 I have already defined, I need to define d and I need to define m, all right. So, I am going to take, oops, all right. So, I am going to take unknown quantities d to be equal to 1, all right, d is equal to 1, and let us say I want to draw this for multiple modes, all right. Okay. For modes going from 1 to 4, all right. I want to calculate f cutoff first, right. F cutoff is m V1 divided by 2d, that is the formula we have, and for each value of m I will be having m multiplied with V1, all right, divided by two d. could also do without the dot over there. They are all just simple numbers. You can just make m multiplied by v1 divided by 2d, right. Phase velocity, the formula that we have is, okay, let us also define another term, right. Operating frequency has to be defined. So, the operating frequency, I want it to go from 0 all the way to 10, right. In this case 10 is a high frequency, that is it. Okay. So, I have V1 divided by square root of 1 minus f cutoff divided by f I am using the dot slash dot to the power because f is an array, alright. F is having a, it is a vector, it is having 0 to 0.1 to 10. So, it has a, I want to take each element and multiply. To be double sure, for everything I am putting dot slash dot to the power, etc., right. So, it will take element by element and calculate this. Okay. Is there an extra bracket? 1, 2, okay. Yeah. Yeah, I think it's fine. Vg was, I think it was not divided, but I think it was just multiplied. Yeah. So, I just changed the sign over there. Then I just need to make a couple of plots. Okay. So, I will just make so frequency comma the phase velocity, right. Because it is in a loop, I want to plot for m equal to 1 through 4 all on the same plot. I am just saying hold all the plot parameters as it is, right. So, x axis will be frequency, y axis will be the phase velocity in this case, right. And I think here as the number of modes changes, it is going to draw different plots. I do not want to do this legend string because it is too much of coding. So, I will just say after each plot, I will just click the button, alright. Then I know that it is going from m equal to 1 to 4, then I will figure out which is corresponding to 1 and 4, because that is only one line of code, and I will just write that as wait for button press, right. It will just wait for me to click my mouse button on the current active figure, and that saves the trouble, right. Okay. And to make it a little bit more interesting, what I will do is I will also put f comma Vg, right, the same plot. So, I will have phase and group velocity. Maybe first I will do phase velocity to distinguish between the two, right, and then I will come to the phase and the group velocity. So, I will just run this, right. So, I am having a plot for the phase velocity, and this should be corresponding to m equal to 1, alright. So, it starts from here and then asymptotically goes to 1. So, at very high frequencies, the phase velocity has become equal to 1, which is my defined value of V1. At very low values of operating frequencies, it seems to be going all the way to infinity. It seems to be following the trend. I will make a click. Okay, I have the next plot. So, this red plot has come in new, alright. It shifted to the right and it has some characteristics like this, alright. So, here also I notice that asymptotically it arrives at the velocity of the homogeneous medium, and it starts at infinity, m equal to 3, m equal to 4. So, it looks like as I keep on increasing the modes, right, the plot is going to start towards the right, and it is always, it is going to go towards asymptotically arriving at that particular medium's homogeneous velocity, right. I am just going to make it, right, make it a little bit more interesting, and I am just going to make it comma Vg, also now going to plot group velocities. Now I know that the phase velocities were having this kind of a shape, right? They were going like this, right? Whatever other shape comes should be due to the group velocity, right? Okay. Now I have something going on here. I remember that this was phase velocity, all right, and phase velocity was higher than 1, okay. It was higher than 1, all right. In fact, it was going all the way to 2, it could go to infinity also, right. And then it was asymptotically coming to 1, that was phase velocity. The group velocity is lower than 1, in fact, it is 0 in the beginning, and then it is going towards asymptotically to the value which we have defined as V1 in our program, right. So, it is starting with low value of group velocity and going all the way and becoming V1. So, I will just make a click for the next higher mode, right, and it keeps going. So, I know that this plot corresponds to the group velocities because it is asymptotically approaching 1 from 0, okay, and the other plot is going to be for the phase velocity. Okay. So, this is how the phase and the group and the phase velocities would look like for your parallel plate waveguide, all right. So, you are having some curves that tell you that the velocity is changing with the operating frequency. So, you have kept the f cutoff fixed, that means you have kept your for a given mode the configuration of your parallel plate is fixed, D is fixed, medium filling in is fixed, but just with respect to frequency you are having different group and different phase velocities. There is only one more detail that we have to add over here. Okay. Now, M we started with 1 going all the way to 4, all right. We can always make M equal to 0 to 4, okay, and then redo this, all right. We are talking about M equal to 0. Now, I get a horizontal line straight, which means the phase velocity and the group velocity have been plotted here, they are one on top of the other and they are forming a horizontal line at the value of the velocity equal to 1. For M equal to 0, in the case of a parallel plate waveguide, the phase velocity and the group velocity is equal to the velocity in that medium itself, and the waveguide is not dispersive, it is non-dispersive, all right. This means that something is happening. If you go back to the expressions for the fields that we had before, you will notice that if you substitute M equal to 0 for the electric field expression that we had before in the parallel plate case, you will notice that you will not have a component of electric field in the direction of travel, it will become 0. Similarly, for the magnetic field, you can use the curl equation, find the magnetic field, and if you try to plug in M equal to 0 there, you will have no component of magnetic field along the longitudinal direction. You will notice that electric field and magnetic field will be transversal, they will also be perpendicular to each other and perpendicular to the direction of travel. This means that M equal to 0 corresponds to a plane wave or a TEM wave, the case that we are already familiar with, all right. In this particular case, what happens is you are launching a plane wave and you are keeping a waveguide, and the waveguide has no effect on the plane wave because it is traveling as it would in a homogeneous medium with a constant velocity, all right. So, whether you had kept the waveguide or not, the phase and the group velocities will be the same as air, all right. Secondly, if you kept the waveguide or if you removed the waveguide, there is going to be no dispersion, okay. So, what does this mean? This means that even though you can write down the fundamental mode of a parallel plate waveguide to be M equal to 0, it corresponds to a case where there is no component of electric and magnetic field along the direction of travel, it represents a pure plane wave, and the waveguide does nothing to it, which means the intrinsic impedance of the waveguide is equal to the intrinsic impedance of air, does not reflect, does not scatter, does not do anything. What does that mean? That means that the waveguide, even though you have kept two infinitely long sheets in vacuum and you are launching a plane wave, the plane wave does not see it. It just sees the waveguide to be purely transparent. Okay. So, a waveguide with M equal to 0 is just going to become transparent to a plane wave going in that medium for a parallel plate waveguide, right. and if you have higher frequency, higher modes, then only you are going to be having some dispersion coming into the picture. Okay. So, these are some two small details that we had to see. Now, I think there are a few more things with respect to the rectangular waveguides that we have to cover in the next class, right. And following that, we will be talking very briefly about waveguides with metals at the boundaries of the facets also. What if you took a waveguide and you put a metallic facet at the input, metallic facet at the output, you will have a what is known as a cavity. Suppose you did find a way to excite it with the source from inside, the wave has nowhere to go, it should keep being built up in the cavity. We will just see very briefly about it, right, very briefly, not in great detail. And then we will try to have some experiment where we can estimate, all right, standing wave patterns, frequencies, etc. We will do some experiments and then try to get an understanding for these standing wave patterns. Okay. So, I will stop here, we will meet in the next class.